When we first started this unit, we talked about 4 properties of waves that were exhibited by EMR, showing that EMR is in fact a wave. One of them was diffraction. Diffraction was the spreading out of a wave. Waves spread out around a barrier or through an opening. So does EMR. Therefore, if EMR exhibits diffraction, then EMR must be a wave. The next one was interference. Interference is a property of a wave. When we have 2 waves coming together, we get either constructive interference or destructive interference. Now, EMR exhibits interference just like other waves do as well. Therefore, EMR must be a wave. Another one we had was polarization. Remember, polarization was the filtering out of certain components of a wave. If you have a wave that's going through a polarizing filter, you can filter out all but the horizontal or all but the vertical component of the wave, whatever. Polarization is a property of waves, but it's exhibited by EMR. Therefore, EMR must be a wave. The last one was refraction. Refraction we talked a little bit about last year. We talked a little bit more about it earlier in this unit. Refraction is the bending of a wave. When a wave changes direction, we call it refraction. Now, clearly, by the photo on the board right now, you can see that EMR, specifically in this case, visible light, exhibits refraction, this property of a wave. Therefore, EMR, according to this observation, must be a wave. How do we know that this EMR, in this case, the visible light, exhibits refraction? Well, you got a pencil sticking in the water, and assuming this pencil isn't some kind of trick where the pencil actually is bent, then we have a perception here that isn't really happening. The pencil is stuck in the water. Light reflects off of the pencil, bounces off of the pencil, and then leaves the water-air boundary. When it leaves the water-air boundary, it bends. Now, the reason it bends, we'll talk about that in a few moments, but it does. It bends. And that tricks our eyes and our brains into thinking the pencil is in a place other than where it really is. We're not smart enough instinctively to know that light can change direction. So when light goes from water to air and changes direction, we perceive the light as if it was always traveling in a straight line. The direction that it enters our eyes from, we think that it's always traveled from that direction. Really, it hasn't, but that tricks us into thinking this part of the pencil is in a place where it's really not. Now, we have a little analogy here to help us to understand why refraction takes place, why this change in direction takes place. We've got a parking lot here. It's paved with nice, fresh pavement. And then we've got this swamp here with a half a meter of water in it. We've got a bunch of soldiers marching on this pavement, in stride as soldiers do. We've got 5 soldiers. If we're looking at these soldiers from above, they appear to be kind of like a wave front. Now, soldiers march as soldiers march, right? They march in stride with each other at the same speed. It doesn't look very good in a parade if soldiers are all in a step with each other and they're all marching at different speeds. When soldier 1 marches for, let's say, 5 seconds, soldier 1 ends up in that position. Soldier 2, soldier 3, soldier 4, marching in stride with each other. They all end up beside each other, except soldier 5. Soldier 5 doesn't end up quite as far. How come? Because he or she is now in the swamp, can't go as fast. So if we draw that line that joins these soldiers together, it now looks something like this. There's a bend in it. 5 seconds later, soldier 1 is up here. Soldier 2, soldier 3. Soldier 4 is just entering that swamp, so it's slowed down a little bit. Soldier 5 is firmly in the swamp now, and it looks something like this. Okay, let's go soldier 1, soldier 2, soldier 3, just barely in the swamp. Soldier 4 has been in the swamp for 10 seconds now. Soldier 5, same thing. So if we draw that line that joins them together here, it looks something like this. If we pretend this band of soldiers is a wave front, then the wave front was traveling this way, and now the wave front is traveling this way. So, as a result of a change in speed of a wave, this is important. As a result of a change in speed, this is what affects everything. As a result of a change in speed, the direction changes, or we'll say theta changes. If V goes up, theta goes up. If V goes down, theta will go down. As a result of a change in speed, the direction changes. What else changes? When you look at this diagram, and if you remember from yesterday, what also changes as a result of the change in speed? What is it? The wavelength, yeah. You can see the wavelength right here is a certain value, but the wavelength over here, the corresponding wavelength over here, is smaller. So as the speed increases, the angle increases, so does the wavelength. As the speed decreases, the angle decreases, so does the wavelength. What doesn't change? What is it? Yeah, we have 4 waves per 20 seconds right here. We have 4 waves per 20 seconds right here. So the frequency isn't going to change. The frequency stays the same. Now, we're going to give you in a few moments here an equation that relates together these 3 variables: speed, theta, and lambda. Okay? It shows you the relationship between those variables. Frequency isn't in that, because frequency stays the same. Once the wave has been made, the EMR in this case has been produced, the frequency of that EMR isn't going to change. So the only relationship we have is between speed, angle, speed, theta, and wavelength. Okay, let's define a term here beyond refraction. Let's define this index of refraction. The index of refraction, we said this yesterday, right? The index of refraction, really, the way we think of it at least, it's just a measure of how much light bends when the light goes from one medium to another. So if we look back at our analogy here, it's a measure of how much the direction that the soldiers were marching changed. If we look back at our photograph on the first page here, it's a measure of how much the light bent when it went from the water to the air. But that's not the technical definition of it. That's just kind of the way that we understand it. Remember, we defined momentum loosely as how hard it is to stop something, but the real definition was the product of mass and velocity. We're going to define the index of refraction loosely as how much light bends, but the real definition of the index of refraction is a ratio. It's a ratio of the speed of light in a vacuum to the speed of light in the medium. So in other words, it's the ratio of C, the speed of light in a vacuum, to V, the speed of light in the medium. Now we're going to write that mathematically as an equation. An equation, by the way, that does not appear on your data sheet. We're going to say N, which is the index of refraction, is going to be equal to C over V. Remember earlier in the year we talked about comparing things and finding a ratio? What's a synonym for compare? A synonym for ratio? Starts with a D. Divide, right. So if you want to find a ratio between the speed of light in a vacuum to the speed of light in the medium, let's divide the speed of light in the vacuum C divided by the speed of light in the medium V. Now, C is always going to be 3.00 times 10 to the 8 meters per second. And V will always be less than or equal to 3.00 times 10 to the 8 meters per second. If you're in air, well, the speed of light in air is pretty much the same as it is in a vacuum, so V would be 3 times 10 to the 8. If you're in water, the speed of light would be about 2 times 10 to the 8 meters per second, less than the speed of light in a vacuum. If you're in diamond, it's going to be dramatically less. I think it's something like 1.4 or something like that, times 10 to the 8 meters per second. So it's always going to be either the same as C, or it's going to be smaller than C, which means that the value of N will always be greater than or equal to 1. Good. Greater than or equal to 1. The index of refraction for a vacuum would be 3 times 10 to the 8 divided by 3 times 10 to the 8, or 1. The index of refraction for air would be 3 times 10 to the 8 divided by 2.999 whatever times 10 to the 8, so effectively 1. The index of refraction of glass would be 3 times 10 to the 8 divided by 2 times 10 to the 8, which would be 1.5. Make sense? What are the units for index of refraction? What are the units? I see somebody doing kind of this. I'm not sure if that means there are none or whether it's off with your head. I'm not sure. I'm going to assume that it means there are no units. There are no units. Yeah, it's meters per second divided by meters per second, which cancel, right? Which gives us no units. So we got a number that's equal to or greater than 1, and there are no units associated with it. So index of refraction is how much light bends when it goes from one medium to another. It's the ratio of the speed of light in a vacuum compared to the speed of light in the medium. But it gets a little trickier because the index of refraction is a little bit different for each material depending upon what type of EMR you have, what frequency of EMR you have. So for instance, if you have a piece of glass, a prism like over here on the wall, that glass prism doesn't change. But if I shine white light through it, white light which consists of all the colors of the rainbow, right? Red, orange, yellow, green, blue, indigo, and violet. Each different color will actually refract a different amount because the index of refraction of the glass is slightly different for each different frequency or for each different color. Now the effect of that is a phenomenon called dispersion, which is the phenomenon that we see on the Pink Floyd album, The Dark Side of the Moon. It's dispersion. When white light, which is all the colors combined, white light coming from the light bulb that you see on the ceiling here, it's all the colors combined. When that passes through each of those colors, because there's a different index of refraction for each of them, each of the colors bends a slightly different amount. And the effect of that is that it splits up. You end up seeing white light going in to the prism, and you end up seeing a rainbow coming out of the prism. Now, what's the order of the colors? Well, it's Roy G. Biv. Red light refracts the least. Violet light refracts the most. In other words, the index of refraction for that prism for red light is smaller than the index of refraction of that prism for violet light. In other words, low frequencies produce a smaller index of refraction and high frequencies produce a larger index of refraction. Does that make sense? I'll tell you what, I don't memorize that. I don't remember that. Here's what I do every time I see a question that asks me to relate the frequency to the index of refraction. I think of that poster on the wall. I picture that album cover, as much as I don't even like that album. I picture that album cover in my head. And I can see that red light is on the top, violet light is on the bottom. Therefore, red light bends less than violet light. Therefore, the index of refraction of the glass must be less for red than it is for violet. Low frequencies produce smaller indices of refraction. High frequencies produce larger indices of refraction. Everything I just said comes from me just picturing this diagram in my head and then figuring out the relationship between frequency and index of refraction and so on. This phenomenon, by the way, where light splits up as it goes through this prism or some other refractive material, is called dispersion. We see this. We see this often. When there's moisture in the atmosphere, the moisture acts as a prism. And when white light coming from the sun passes through that prism, which is the moisture in the atmosphere, we get a rainbow. That's caused by dispersion. One of the best examples of dispersion happening other than a rainbow that I've ever noticed was actually in this building. I was walking at a school one day after school. The angle just happened to be right. The sun just happened to be in the right place. Walking past the cafeteria. When you walk past the cafeteria, which is right here, there's this triangular glass display cabinet. Light was passing through the corner of this triangular glass display cabinet, and on the floor was this great example of a rainbow. This bright Roy G. Biv rainbow caused by the dispersion of white light passing through the corner of this display cabinet. Each different color refracted a different amount. Does that make sense? We already said this. higher frequencies disperse more than lower frequencies. But again, that's not something that I memorize. Okay, I figure that out by picturing the diagram. Okay, if you're not a visual person, okay, then maybe you remember that. Okay, but if you're like me, then it's easier for me to remember this picture than it is to remember that statement. Here's the equation that relates all of this stuff together. It's called Snell's law, and it's kind of an ugly looking equation, but when we kind of dissect it, it's not so bad. It says sine theta 1 over sine theta 2 equals, thank you, V1 over V2 equals lambda 1 over lambda 2 equals N2 over N1. What does all this stuff mean? Well, I'm going to draw a picture to help explain that. This line is going to be our boundary between, let's say, medium 1 and medium 2. Medium 1 is where the light is coming from. Medium 2 is where it's going to. We're also going to draw a dotted line that is perpendicular to the boundary. We're going to call that a normal line. In Physics 20, we use that term normal force. Normal line, normal force. The normal force was perpendicular to the surface. The normal line is perpendicular to the boundary. In physics, normal means perpendicular, 90 degrees. So this is our normal line. It's just a line that we use as a reference to measure our angle from. We're going to say here that the light, the EMR, the visible light, whatever it is coming from medium 1, and it's going into medium 2. When it does that, it changes direction. It bends. You can see the change in direction there. We're going to call the index of refraction of this material up here N1. The index of refraction of this material down here will be N2. We're going to call this theta 1 the angle of the incident line as measured from the normal. We're going to call this one theta 2. That's the angle of refraction, we call it. The second angle, the angle that it's going into. You can notice that theta 2 is smaller than theta 1 here. We'll talk about the implications of that in just a second. V1 would be the speed up here in medium 1. V2 would be the speed down here. Lambda 1 would be the wavelength up here, and lambda 2 would be the wavelength of the EMR down here. Notice what's not there? Frequency. Why not? Because the frequency doesn't change. The angle changes, the speed changes, the wavelength changes because of the change in index of refraction, but the frequency doesn't change. Now, have a look at this equation. The relationships in this equation that we call Snell's law. See if you can answer a couple questions for me. You can see here that when we're going from medium 1 to medium 2, theta is decreasing. Can you see that? Theta 1 is bigger than theta 2, so the angle is going down. Make sense? If theta goes down, what do you think is happening to V? Look at the relationship in the equation. What do you think is happening to V? It's going down. Yeah. In fact, theta is going down because V goes down, right? V isn't going down because of theta. Theta is going down because of V. But it's a similar relationship. If the speed decreases, theta decreases. What about lambda? What about the wavelength? As the speed goes down, speed decreases when we go from medium 1 to medium 2, theta it decreases as well. What about lambda? What is it? It's going to decrease as well. Now, that all happens because of the index of refraction. The index of refraction of medium 1 is something. The index of refraction of medium 2 is something else. Which one is bigger? Does the index of refraction increase or does it decrease in this diagram? What is it? Increases, yes. As a result of n going up, of n2 being bigger than n1, theta goes down, v goes down, lambda goes down. You can tell on the relationship here, that's why it says sine theta 1 over sine theta 2, v1 over v2, lambda 1 over lambda 2, and n 2 over n1. It's an inverse relationship there. As n goes up, v goes down, theta goes down, lambda goes down. Now this table on the right-hand side, you don't need to remember any of these numbers. Okay, if you ever need these, and you will, they'll be given to you somewhere on your test. This one is actually given to you on your data sheet. The rest of them aren't, but if you need them again, they'll be given to you somewhere, probably buried in a page of information in your test. Know that as well that these are averages, because the index of refraction, let's say, of water is 1.33. It can be a little bit higher or a little bit lower depending upon the color of light, the frequency, right? Water has a slightly different index of refraction for each different frequency, but it's not that much. So for most purposes, we can just say it's these values. Make sense? But know that you could conceivably get a question at some point where it says the index of refraction of water, let's say for red, is 1.3301, and the index of refraction for water for blue is 1.3304, or something like that. I don't know what the numbers would be, but something like that. You understand that it could be slightly different for the same medium. Okay? Good? How do we actually use this equation? Well, the good news is there's 4 parts to it, but you're only ever going to need to use 2 parts. We can say sine theta 1 over sine theta 2 is equal to v1 over v2. Or we can say lambda 1 over lambda 2 is equal to n2 over n1. Or we can say v1 over v2 is equal to n2 over n1. It just depends upon what you're given, right? Write down what you got given to you, and then figure out which 2 parts of that equation match the givens the best, and then start subbing the numbers in. Let's take a look at a couple examples here. Example number 1 says calculate the speed of light in a ruby. Calculate the speed of light in a ruby. Well, we're not actually going to use Snell's law to answer this question. We're just going to use the definition of the index of refraction, which is n is equal to c over v. I want to find v. The speed of light in a vacuum is 3.00 times 10 to the 8 meters per second. What's the index of refraction of ruby? I don't know. Let's look it up. The index of refraction of ruby is 1.54. So let's say 3.00 divided by 1.54 gives me a value of 1.95. 1.95 times 10 to the 8 meters per second. You see that what's happened here, guys? The index of refraction of a vacuum was 1. Of ruby, it's 1.54. So if you go from a vacuum to ruby, the index goes up, the speed went down. Make sense? We know that the speed of light in any material has to be either equal to 3 times 10 to the 8 or less than 3 times 10 to the 8, right? And this is clearly less than 3 times 10 to the 8. Let's do example 2, and then we'll call it a day. Light passes from water to ice, so liquid water to ice, at an angle of 40 degrees. Determine the angle at which the light struck the water/ice boundary. Let's draw a picture of this, okay? If you try to do this without drawing a picture, there's a pretty good chance you're going to mess up on it. We're going to say this is the water. We're going to call this medium 1, and when this is the ice, we're going to call this medium 2. The light is passing from water to ice. Now, what's going to happen to theta here? Let's look back at our indices of refraction for a second. The index of refraction for water is 1.33. For ice, it's 1.00. What did I say? 1.33 and 1.31. So as we're going from water to ice, the index of refraction goes down. Not by a lot, but by a bit, right? If n goes down, what's going to happen to v? As n goes down, v will go up. As n goes down, v will go up, lambda will go up, and theta will go up. Yes. So we're going to find that the light bends this way. In the diagram that I drew for you a few minutes ago, it bent this way. We know that it bends the other way this time because n went up. So what do we got here? It passes at 40 degrees. And we want to find this angle right here, theta 1, the angle at which it struck the water/ice boundary. We're going to use Snell's law for this, but only two parts. Sine theta 1 over sine theta 2 equals n2 over n1, or sine theta 1 over sine 40 degrees equals n2, which is 1.31, over n1, which is 1.33. Now, the one thing about these questions is if you're conscious of reasonable answers, you look at your answer and you check to see if it's reasonable, you should be able to tell. Like, you should be able to tell if you've made a mistake. It gets a little bit tricky with all the numbers here, but you should be able to tell if you've got them right, because we should expect theta 1 to be smaller than 40 degrees, right? The angle increased because n decreased. Let's figure this out. 1.31 over 1.33 is equal to 0.9849. We times that by sine 40, and we end up getting sine theta 1 is equal to 0.63312. 1.31 over 1.33 times sine 40. Now we're going to take the inverse sine of that, second function sine, and we get a value of 39.3 degrees, or round to 2 digits, 39 degrees. Is that a reasonable answer? N went down by just a little bit. So we would expect theta to go up by just a little bit. Did it go up? Yeah, from 39 to 40 by just a little bit.